rockin' all night long. Feel the bass coming on strong.
Well, continuing on with the AC syllabus, we've learnt so far about the phase difference between voltage across different components in a circuit that has reactive component and has resistive component. And I've illustrated this on the board up here, showing that the voltage across the resistor and also the current across the capacitor in this RC circuit, and the current in general, because it's a series circuit and the current is shared by all three components. So IC, IR, I circuit, VR are all leading the supply voltage, and the supply voltage is leading the voltage across the capacitor. And this is really a little bit difficult to absorb the first time you see this, and it does require a lot of thinking. But this illustration is the key to success in studying and learning about AC. Learning about this phase difference. And then if we put this illustration between our different signals and the time delays between the signals, if we put that into a diagram here which shows the vectorial representation of those different signals, we can see then that we've got the voltage on the resistor leading the voltage on the capacitor by that 90 degrees that we've talked about in class earlier. And the resultant between these two vectors, and I guess I should put a arrow there, is this point here, and that represents the supply voltage. And then again to say this angle here, that the current in the circuit is leading the supply voltage, is the phase angle of the actual circuit, the phase angle of the circuit. And of course here we have theta 1, which is 90 degrees minus the phase angle, and that's the difference between the voltage on the capacitor and the supply voltage. Now today what we're going to do is construct a circuit using one resistor and one capacitor with an 8 volt peak to peak sine wave supply coming from our signal generator, and we'll use various frequencies. We'll construct a table and we'll come up with the voltage across the resistor and the voltage across the capacitor. Now, something that's really difficult, I do believe, to understand about a circuit like this is, why do we actually have to construct the circuit twice? Why do we have to build it, take some measurements, like say we make this circuit number 1, and we set the 8 volts peak to peak here with channel 1 of our oscilloscope, and then we measure the voltage across the resistor with channel 2 of the oscilloscope? That's fine, but I always get asked, why can't I just somehow move the oscilloscope probes without rebuilding the circuit and measure the voltage across the capacitor? Well, you can't do that, because on the oscilloscope we have a situation whereby we have the oscilloscope lead with the active terminal in the middle, and the outside braid of that oscilloscope lead is connected to ground. So if we were to measure the voltage across that capacitor by using this type of a setup, and say we put the active side there and we put the ground there, what have we done? Well, we've got ground on this side of the resistor, we've got ground on the top of the resistor, so effectively what we would have ended up with is a short circuit across the resistor. That's certainly not desirable, and it certainly won't work for us. So what we have to do is make some changes to the circuit. So with the various frequencies that we plot, I think there's about 8 different frequencies called for on the lab sheet, and we're going to plot those, ensure that we maintain our 8 volts peak to peak across the signal generator, and we're going to measure VR at each one of those frequencies and log it down. Then we're going to deconstruct the circuit, and we're going to reconstruct it this way. 1K resistor leading and the capacitor in shunt. And then of course channel 2 of the oscilloscope will go to there, and channel 1 will still be here. The circuit is going to have the same characteristics. R hasn't changed in value, C hasn't changed in value, but now it enables me to measure VC as opposed to measuring VR. So circuit number 1 for measuring VR, circuit number 2 for measuring VC. And then we'll do exactly what we did. We'll maintain our 8 volts peak to peak. We'll go through the 8 different frequencies, and in our table we'll write down what the voltage is across that capacitor. And then further on in the lab, we'll use those figures, we'll determine the circuit current from the voltage across the resistor, and knowing that we have in fact a 1K which does not change, and then we'll be able to plot a graph of XC against the other coordinates on the graph. So I hope that sort of explains why we have to rearrange the circuit. There's never a time go by in all the times I've taught this that somebody doesn't ask, why can't I just move the oscilloscope to measure VC and VR? Why do we have to rearrange the circuit? So I hope that explains it. If in fact we had an oscilloscope that was battery operated and therefore was not grounded, not a problem. We could simply put it across each component that we wanted to measure. But in this case, with a AC mains operated oscilloscope, which is grounded to all our other equipment, no, we cannot do that. And this hits us all the time in troubleshooting electronic circuits. We have to remember about the ground lead on the equipment and what we're measuring and where to put that ground lead. You never want to put it onto something that is actually a high voltage source, perhaps. You're going to end up in big strife, lots of sparks and lots of blowing fuses, and yeah, you're not going to feel real good about it. So let's get on with the lab then, and then we'll compare the results that we get in this lab. This is Greg Moore for New South Wales TAFE. So continuing on, here's the first part of the lab where we use the capacitor in series and we have the resistor in shunt. And of course here the channel 2 of the oscilloscope is measuring the voltage across the 1K resistor, and channel 1 of the oscilloscope was measuring the voltage from the source. In the second figure we have rearranged the circuit components, and now we're measuring the voltage across the capacitor and ensuring that the voltage from the supply remains the same on channel 1. Here's the lab results. You might like to pause the video at this point and examine the lab results. Have a look at VR. IT is a calculated value based on VR and the value of R itself. And there's VC. And of course we've been able to work out XC from those results. And finally, here is our graph. The graph is asymptotic. It's XC against frequency. There, and of course we plotted several frequencies between 10 and 100 kilohertz.
Rock to the rhythm all night long, feel the bass coming on strong.